Okay, so this is the practice exam for lecture exam 2. It's actually not a practice exam. This is just a compilation of practice questions that we're going to look at that are examples of what you might see on the exam and examples of styles of questions you might see on the exam. So we'll jump in here with the first one. This one is a straightforward metathesis reaction question where what we're going to do is we're going to look at the molecular equation and then the net ionic equation for a variety of different reactions. So the first one is the reaction of barium hydroxide and hypochlorous acid. So this is an acid-base reaction, so we can write the two species, barium hydroxide aqueous plus HClO aqueous. And since it's an acid-base reaction, we can predict the products. That's going to be barium ClO, and this is going to get a 2. We can see that ClO anion must have a -1 charge because it's with the H plus ion. So we know that we're going to need 2 ClOs for every barium, and we can add to this H2O, which is the other product. This is going to be liquid, and this is going to be aqueous. So the H2O comes from the reaction of the hydroxide with the protons, and that forms water. And then if we want to balance this out, we know that we're going to need 2 HClOs, and this will produce 2 H2Os. Okay. So in this case, the reaction is the reaction of a strong base with a strong acid. So both of these will be separated in solution. So we can summarize this as the reaction of H plus aqueous plus OH minus aqueous gives H2O liquid. Now on the exam, if you needed to, you could always flip the exam over or ask for a little extra space or room to write out the full ionic equation if you have to, but generally speaking, you should be able to kind of see the net ionic equation after all the practice you've had. Now, one thing I want to point out, though, is even though there are 2 OHs and 2 H+, which one might think would give you 2 and 2 and 2, because the 2 can all be divided by 2, the true net ionic equation is just the H plus OH minus gives H2O liquid. So I just wanted to point that out. Okay, so the next one is the reaction of magnesium carbonate with sulfuric acid. So this is going to be a gas-forming reaction. So magnesium carbonate solid plus H2SO4 aqueous. And this is going to give the following product. So we know already that we're going to get magnesium sulfate. So by switching the ions, this will be aqueous, that's soluble. And then in this case we would get H2CO3, but we know that H2CO3 is not stable. That is carbonic acid. This will decompose to form H2O liquid plus CO2 gas. Okay, now writing the net ionic equation. In this case, if you were to write the full total ionic equation, the magnesium carbonate is not going to break up because it's a solid. So this has got to stay together. And then we have 2 H plus aqueous that are going to react with it. And then this is going to give us magnesium 2 plus aqueous plus H2O liquid plus CO2 gas. Okay, so what winds up happening here is the sulfate becomes a spectator ion that gets eliminated out of the net ionic equation, and then you get something that looks like this. So the solid does persist. Okay, so the next one is aqueous sodium acetate. So that's going to be NaCH3COO. So I remembered that the acetate anion looks like that. You could also write this as C2H3O2. That's fine. However you want to remember it, I would accept either one. And then we're going to add to that HNO3 aqueous, which is nitric acid, and we're going to predict the products. Now, a lot of you may say, oh, NaNO3 and CH3 and acetic acid are both soluble, so no reaction is going to take place. That is actually not true. In this case, the reaction that's going to take place is as follows. We are going to get NaNO3, aqueous, and we are going to get CH3COOH aqueous. Keep in mind that acetic acid is a weak electrolyte. It doesn't fully break up. So in this particular instance, we do write this as the final product. Whenever you produce a weak electrolyte, that is going to be written as the final product. So this is not going to break up into its ions completely. That's why that appears here. So for the, oops, I forgot my aqueous there. So for the net ionic, we're going to have H3COO- aqueous plus H plus aqueous is going to give our weak electrolyte CH3COOH aqueous. And then the last guy on this chart is strontium chloride, which is SrCl2 aqueous with potassium sulfide. So that is going to be K2S aqueous. Okay. Remember, sulfide is just the S2 minus ion. So you have to balance that out. And I know strontium is a 2+, so that's how I came up with these guys. So if we do our metathesis reaction dance, we get strontium sulfide and potassium chloride. And strontium sulfide is, in fact, a insoluble ionic compound, so that will be a solid. And then that will give us 2 KCl here as aqueous. So our net ionic equation in this case will be Sr2 plus aqueous plus S2 minus aqueous will give SRS solid. Okay. So again, with the net ionic and molecular equations, the key thing to remember is that to go back to your experience in the lab where we did a lot of these, and to consider what's going on. So consider what the solubility is, what the driving force is. Are you producing a weak electrolyte? Are you producing a gas? Are you producing a precipitate? And then from there, you can kind of predict what the products are going to be and predict what the things are going to be. So you're going to have to know your solubility rules for this test, and the solubility rules will come into play largely in the metathesis reactions. Alright, so the next one, we're going to kind of switch gears here. So the practice exam is taking us to a different part of chapters 4, 5, and 6. So we're going to go to chapter 5. This is a relative rate of effusion problem. So this is asking, what is the rate of effusion for helium gas if the rate of effusion for argon is 6? Okay. So the only thing that I can recommend is that these questions are typically relatively straightforward. All you have to do is know the rate of effusion equation, which is the rate of effusion for some gas, let's say A, divided by the rate of effusion for some gas B is going to equal the square root. And as we discussed in class, this is inversely proportional. So if you think about it, the heavier the thing gets, the heavier the gas gets, the harder it's going to be for it to effuse. The bigger it is, the slower it's going to effuse. So we get an inverse proportionality where it's going to be the molecular weight of B over the molecular weight of A. So in this case, all we have to do is plug in to this equation, and we should be all set. So actually, in this case, we can set this up where we just write down our variables. So we have argon is 1, so the molecular weight in this case, I'm going to grab my periodic table. The molecular weight of argon is 39.9 grams per mole, and its rate is equal to 6. I don't give you any units, so don't worry about it, that's fine. And the gas molecule B is going to be helium. So in this case, that's going to have a molecular weight of 4 grams per mole. Okay. And we're interested in what is the rate. So in this case, we can set this up in a relatively straightforward manner. But before I even do this problem, I just want to highlight one thing. You should be considering what's going to happen already. So we said that for bigger things, for heavier gases, like argon in this case, they're going to go slower. So in the end, we would expect the rate for helium to be larger, some larger number than 6. So to plug this in, to make life easier, we're going to make that helium is going to be gas A, and argon is going to be gas B. You'll see why in just a quick second. But it doesn't matter. You can plug it in any way you like. So if we follow that pattern, we can say, okay, so we can say that rate A, which is the thing we don't know, divided by 6 is going to equal the molecular weight of B, which is 39.9 grams per mole, divided by the molecular weight of A, which is 4 grams per mole. Now, here you can see why I selected it to be this way. It's because when you rearrange things, all I have to do is multiply this by 6. So we can get rate A. So if you plug this into your calculators, the way that I'm going to plug this into my calculator is like so. So I am going to take the square root of 39.9 divided by 4. Okay, so that's this term, and then I'm going to multiply it by 6, and I get a rate equal to 18.9. Now in this case, the sig figs are a little wishy-washy because you only get one sig fig from the rate. But in this particular instance, as long as you write down that you get a rate of 18.9 with a line underneath the first digit for the sig figs, that should be perfectly fine to show that you know what's going on. And as you can see, this is kind of a good self-check because you can see that the rate is definitely higher in the case of the helium, which is a smaller molecule. Okay, so moving on, we're going to go on to question 3. So now we're switching back to chapter 4 for this particular question, and this is just a straightforward molarity question. So there's really not too many tricks to this. The only thing that you really have to understand is that we have to do a little bit of stoichiometry here to make sure that we get everything correct. So the first part says a solution is prepared by dissolving 0.99 grams of aluminum chloride, they give you the molecular weight, to give 113.3 milliliters of aqueous solution. So calculate the molarity of the Cl- ion. So I know that in the end, what I need to know is the number of moles of Cl- divided by the total volume. So this is going to be the liters of solution. And already I have the total volume, which is going to be 113.3 milliliters. So we're going to convert that to liters to get 0.113.3 liters. So this is going to be the molarity. So now the only thing I need to get is the moles of the Cl-. So to do that, we're going to start over here our 0.99 grams, and then we can convert this to moles using the molecular weight, so 133.3 grams for every 1 mole. And then we know that for every 1 mole of aluminum chloride, we have 3 moles of Cl- ion. Now the way that I deduce this is because if you want to think about it, AlCl3 is soluble, and this will go to Al3 plus 3 Cl-. So you have to keep that in mind when you're doing this, and then that way you can get the correct number of moles of the Cl- ion. So if we plug this into our calculators, 0.99 times 3, and then we divide by 133.3. That's going to give 0.022 3 moles. So we plug in 0.223 moles up here, making sure that we keep track of our sig figs, and then we're going to get 0.022. Well, we could just take the answer and divide that by 0.1133. So this is going to give me a concentration of 0.197 molar or moles per liter. So my final answer here is going to be 0.197 molar for the Cl-. Okay, so now the second part of this question is a dilution problem, where we take some amount of that initial solution and we dilute it to 82.8 mils, calculate the concentration of the aluminum ion in solution. So there's a couple of different ways you can start this problem, but thinking about it, what I would do is, first things first would be I need to know what the concentration of my aluminum ion is in the solution before we do the dilution. So again, I'm just going to quickly go through and go back and just quickly calculate what my concentration of the aluminum ion is. So that's going to be 133.3 grams per mole of AlCl3. And in this case, instead of it being 1 mole of AlCl3 to 3 moles of Cl-, we're just going to do to 1 mole of Al3+. And this will just give me my starting number of moles, which we will calculate as 0.99 divided by 133.3. So we get 0.00743 moles. And then we can go back, and just like we did in the first problem, we can calculate the concentration of that initial solution in terms of the Al3+, just by taking the 0.0743 moles and dividing it by the 0.1133 liters. So all I'm doing here is just basically doing what I did in the first problem, except because we're interested in the aluminum ion, I'm just setting it all up again for the aluminum ion so that I have the right answer. So to do this calculation, we can just simply divide the 0.00743 by 0.1133, and we get 0.0656 molar aluminum 3+. Okay, so once you have this, then you can set up a simple dilution calculation. So if you remember with dilutions, it's the key equation is M1V1 is equal to M2V2. So using your initial concentration, so we can kind of go through here and pick out the different variables. So we're taking a 21.7 mil solution portion of the solution. So that's this solution up here. So that's going to be 0.0656 molar. And we're taking 21.7 mils of that. And then we're going to set this equal to the concentration, which we don't know, in a solution with a volume of 82.8 mils. Okay? So if we solve for x, we can calculate that directly, which is going to be 0.0656 times 21.7, and then we can divide that by 82.8, and we get 0.0172 molar. Okay. So just carrying my sig figs all the way through. So the final answer in this case would be 0.0172. So the only thing that's a little tricky in this case is in the first one they ask you for the concentration of the Cl- ion. In the second one you kind of have to do a little bit of both. You have to calculate the concentration of the aluminum 3+ ion and then do a dilution calculation. Overall though, it's really not anything too complicated. It's just all the simple steps involved in solutions, with the exception of you just got to keep track of what you're talking about. Now here's another good example of a solution calculation where it's not really anything too difficult, it's just you got to keep track of what's going on. So in problem 4 it says a solution of 5 mils of 0.050 molar HCl is combined with a solution of 30 mils of 0.15 molar HCl in a beaker. So what you're doing in this case is if you draw your beaker, you have two solutions that are going in. One is going to be this set, so you can kind of draw an arrow. The other one is going to be this set, so you can kind of draw an arrow. And then in the end, these two solutions are going to be combined into that beaker. So the way that I would approach this is, well, by putting in 5 mils of a 0.050 molar solution, I'm putting in some number of moles of HCl. And then again, I'm doing the same thing here. By putting in some amount of this concentration of HCl, I'm putting in some other amount of moles. So if we combine the two amounts of moles and divide by the volume, we should have the total concentration, right? Because in each case, this amount of moles and this amount of moles are going to be in some new volume, which is going to be the sum of the two volumes. So basically what I'm kind of setting up here is the following. So I can say that the molarity final is going to equal the number of moles from solution A, we'll call this one solution A, plus the number of moles from solution B, we'll call this one solution B, divided by the volume of A plus the volume of B. Okay? So if we can sort of fill that all in, we can make a head start. So on the bottom, we can already fill this in. This is going to be 0.005 liters plus 0.0300 liters. So already we have the bottom. Now all we have to do is calculate the top. So for the top, we just need to calculate the number of moles coming in from each. So we know that molarity is equal to the number of moles divided by the volume. So in each case, if we take the moles and we multiply it by the volume, we can get the number of moles. So I'm going to do that so N of A, I'm going to say is going to equal the molarity of A, which is 0.050 molar, times the volume of A, which is going to be 0.0050 liters, and I'm going to get the number of moles of B, which is going to equal 0.15 molar times 0.0300 liters. Okay? So basically I'm just calculating the moles that are going in from each solution. And if we run this through our calculator, we can get two different numbers. So in the case of the first one, we get 0.050 times 0.005, and we get 2.5 times 10 to the minus 4th. So I'm going to write that guy in here. Keeping track of sig figs, we only have 2 sig figs, so 2.5 times 10 to the minus 4th moles. That's coming from A, and then from B, we are going to get 0.15 times 0.0300. So that is going to be 4.5 times 10 to the minus 3 moles. So if we plug this into our calculator now, and we want to calculate the molarity final, we can do that by doing the following. So we can say 2.5 times 10 to the minus 4th moles plus 4.5 times 10 to the minus 3rd moles divided by 5 mils plus 30 mils. And now remember, I'm converting these to liters because the bottom needs to be in liters. So we get a new concentration of the combined solution of 0.136 molar, where the significant figures is under the 6. Okay, so that's how you do the first one. So that is a little tricky. You kind of have to really understand what's going on with solutions, but the reason why I put this practice question is because it kind of demonstrates what's going on with solutions. That it's not just, we don't just use them as a conversion factor, but we have to think about them in terms of what a solution really is. So in this case, a solution is really just an amount of moles held in a volume. So no matter what you do, as long as you can calculate the number of moles, in this case it's the combined number of moles of HCl divided by a combined volume, but that will always get you to the right answer. So that's really the important thing, and that's the reason why I showed this. Why I showed this particular question in the practice exam, because it really gets you to start thinking about things in a different way. Okay, so in part B, we are now going to do something with our HCl solution. So the combined solution is then titrated with a solution of 31 mils of calcium hydroxide. Calculate the calcium hydroxide solution. So before you do anything, you're going to have to write the balanced equation. So we know in this case that this is going to be calcium hydroxide, and we're going to add HCl, and we're going to get calcium chloride and water. Okay, that's just a standard acid-base reaction. And just to make sure that we balance, we're going to have to balance this with 2 HCl's and 2 waters. Now the reason why we need this is because in order to do any kind of stoichiometry, we need to know what the intrinsic relationships are with the equation. So in this case, it says the combined solution is titrated with a solution of 31 mils of calcium hydroxide. Calculate the molarity of the calcium hydroxide solution. So basically what this is saying is this solution that we have, so we have 0.136 molar and we have 35 milliliters of it, so 0.0350 liters. If you take this solution and react it with a solution of 31 milliliters of calcium hydroxide, you reach the end point. So basically what that's saying is that the number of moles that are in here are fully react with the number of moles of calcium hydroxide. So this is how we would solve any titration problem as we went over in class. So basically what we're doing is we're reaching the end point where the number of moles of this equal 2 times the number of moles of this. So to calculate the number of moles of HCl, we can go in and do our molarity problem. So if we take, so I set this up already, so the number of moles of HCl is going to equal the molarity times the volume, which is 35 mils. So in this case, that is going to give us 0.136 times 0.035. So what we're going to get from that is 4.76 times 10 to the minus 4th moles of HCl. Okay. Now, we know that we reached the end point, so this is fully reacted with this, so we can convert and say that for every 2 moles of HCl, we have 1 mole of calcium hydroxide. So this is essentially what happens when the reaction is complete. We fully used up so that these two things are equivalent. We've produced all products. So now if we calculate the moles of calcium hydroxide, we get this number divided by 2. So that is going to mean that we have 0.00238 moles of calcium hydroxide. And the final step is calculate the molarity. So if we'll just come down here, we'll borrow a little space from the question below. Sorry guys, I guess there wasn't enough space for these. I just threw this together quick, so go ahead and use a separate piece of paper if you have to while you're doing this. But we'll just do the final calculation for molarity. So we know we have this many moles of calcium hydroxide, and we know that we had 31 milliliters of it. So all we have to do to get the molarity is just say, okay, so the molarity is 0.00238 moles divided by the number of liters, which is 0.0310 liters, and we can get a final value of the molarity of the KOH solution doing this division, and we get 0.00238 divided by 0.031. So I get 0.77 molar. Okay, so that's all that you had to do for that one. All it really was in this case was just you have to understand that when you do a titration and the titration completes, that the reaction in this case it fully consumes the calcium hydroxide. We get 100% products. So we can go back then and use the number of moles of HCl to calculate the number of moles of calcium hydroxide, and then just come up with the original concentration. That's fundamentally what a titration is all about. Okay, so the next one is this looks like a gravimetric analysis problem, if I'm reading it correctly. So a metal M was converted to M2SO4 3 The solution of M2SO43 was treated with a solution of barium chloride according to the following reaction. So what they're doing is, okay, so this is a gravimetric analysis problem. So they're taking a metal and dissolving it in sulfuric acid, and then taking that solution of the metal sulfate and precipitating out the sulfate with barium, so they get a solid. So in this case, it says if 1.1043 grams of the metal gave 5.5426 grams of barium sulfate, calculate the molar mass of the metal. So to start this problem, we'll start this problem right over here. The molecular weight is going to be equivalent to the mass divided by the number of moles of M, of the unknown metal M. So we need to calculate, based on the equation, they give us a mass of the metal, so we can plug that in, 1.1043 grams. But we need to figure out the number of moles of M. And the way that we're going to do that is by backtracking through the precipitation equation. So in this case, it says we got 5.5426 grams of the barium sulfate solid. So what we can do is, if we can figure out from the barium sulfate, if we can track back from the sulfate to the M2SO4, we can then calculate how many moles of metal there must have been. So that's what we're going to do here. So the first thing we have to do is we have to get this into moles, because we need to be able to do some stoichiometric relationships. So we're going to divide this by the molecular weight, which is 233.3 grams for every 1 mole of barium sulfate. And then using the stoichiometric coefficients, we know that for every 3 moles of barium sulfate, there is 1 mole of the M2SO4. Okay. And interestingly enough, we do have to do one more. We know that for every 1 mole of the M2SO4, there is 2 moles of the metal M. So just using that one number that they gave us, we can go all the way back to the metal M. So I'm going to plug this into my calculator so that I can calculate the answer. So in my calculator, I'm going to type the 5.5426, multiply that by 2, and then divide by 233.3, and then divide by 3, and I'm going to get 0.0158. Let's see, what's sig fig? So this is 4, and this is 1, 2, 3, 4, 5. So we're going to have 15838 moles of M. So that's 0.015838 moles of M. So I can plug that in up here. 0.015838 moles. And if we do the division, 1.1043 divided by 0.015838, we get a molecular weight of 69.72 grams per mole. And if you look at the periodic table, I'll bet you that that is gallium. Not that you wouldn't have to do that on the test, but just to show you that actually is a real number. That actually is a real metal. So this entire thing was dissolving gallium to make gallium sulfate, and that's how that worked. Okay. So gravimetric analysis problems, again, you're using a metathesis reaction, in this case a precipitation of barium sulfate, to track back and get information about some other compound that you're interested in. Okay, so on the next page we are now switching into, I believe, gas laws. So on this page, let's just let that autofocus. Hydrogen gas is produced from the reaction of hydrochloric acid on zinc metal. So this is going to be HCl plus zinc metal is going to give H2 gas plus zinc chloride. So you guys have done this a number of times in lab and have seen this. So this is something you're quite familiar with. So now what's actually taking place in the problem? So the gas is collected over water. Now that's immediately telling you something right away. So you're producing a gas and it's collected over water. To me, that should be bells and whistles for a Dalton's law of partial pressure problem, where you're going to have to know the vapor pressure of water. So let's read on. So if 144.7 mils of the gas, so let's just write down our volume is 144.7 mils, we automatically are going to convert this to liters so that we are in the standard units. So we divide by 1,000 mils for every 1 liter, so that's going to give 0.1447 liters. It's collected at 19 degrees Celsius, so immediately I'm going to write down the temperature and add 273.15 to get it in Kelvin. So 19 plus 273.15 is going to be 292.15 Kelvin. Make sure you have your sig figs there. And a pressure is 786 millimeters of mercury for the total pressure. So P total is going to be 786 millimeters of mercury. Now, normally you would convert this, but I bet you, as we read on, we're going to have to do something with this. So what is the mass of hydrogen collected? And then here we go. Here's the kicker. So the vapor pressure of water at 19 degrees is 16.6 millimeters of mercury. So what this problem is this is just a classic Dalton's law of partial pressure. So this gas, we collected it over water. So there's water here. Then there's your gas in the sealed vessel. So this gas is actually a mixture of two different things. This gas is a mixture of H2O vapor and your H2 gas. So immediately we have to write out the Dalton's law of partial pressure problem, so that P total is going to equal the partial pressure of the H2 plus the partial pressure of the H2O. Okay? This is basically saying that because there's a mixture, the total pressure is going to be a mixture of the pressure of water plus the pressure of H2. So in order to do anything with the hydrogen gas, we have to calculate the pressure of the hydrogen gas alone. So we can plug in here that the total pressure is 786 millimeters of mercury. We want to know the pressure of H2 gas, and we know that from the vapor pressure that the water is 16.6 millimeters of mercury. So calculating the H2 pressure, we can subtract those two values, and we get 786 minus 16.6. So this is going to be 769.4 millimeters of mercury. So actually, the pressure total becomes irrelevant, so we can cross that out because that has nothing to do with the problem anymore. The pressure of H2 is equivalent to 769.4 millimeters of mercury. And we can convert this to ATMs immediately to get the answer. So this 769.4 we divided by 760. So we get an atmospheric pressure of 1.012 ATM. Okay. So now we have everything we need in order to calculate the number of moles. So from PV equals nRT, we can say that from PV equals nRT, we can calculate the number of moles. So if we rearrange, we get PV over RT is going to equal N, the number of moles. So if we plug in all of our values, we have 1.012 ATM is our pressure. Our volume is 0.1447 liters. Our gas constant is 0.0821 liters atmospheres per mole Kelvin. Okay. And our temperature is the 292.15. Okay. So in this case, we're just going to plug in for everything. So I'm going to multiply 1.012 times 0.1447, and then we'll divide this by 0.0821 times, remember you have to have a parenthesis for the bottom, 292.15. So this gives 0.006. We're going to have 3 sig figs, 6105 moles of H2. And remember, they're asking for the mass of hydrogen, so in the question. So the last thing we just have to do is convert the moles to mass. And we can say that for every 1 mole of H2, there is 2.0 grams, which is the molecular weight. So we just take our answer here and multiply that by 2, and we get 0.0122 grams of H2. And that's the final answer. Okay? And that is the final answer. Alright, so next up we are doing we're doing another gas law problem, and this gas law problem involves some stoichiometry. So it says calculate the volume of HCl at STP when 55.8 grams of lithium chloride reacts with 542.8 mils of 2.87 molar H2SO4. And then they give us the balanced equation. Now, a lot of you guys are probably wondering, why is he giving me information about 2 different reactants? And the answer is because whenever you get information about more than one reactant, you are setting yourself up for a limiting reagent problem. Okay? So in this case, what they give us is they give us information about one reactant, the lithium chloride, and then they give us information about the other reactant, H2SO4, aqueous. So this becomes a limiting reagent problem because we have to see which one of these is going to limit the reaction and limit how much HCl gas we can produce. So we'll set this up like a standard limiting reagent problem. So for the 55.8 grams, we have to calculate in any limiting reagent problem. We have to calculate the number of moles of HCl, which is our product. So in the case of the 55.8 grams of lithium chloride, we are going to calculate the number of moles of lithium chloride using the molecular weight. And then, so we have moles of lithium chloride. And now we can convert lithium chloride to HCl. So we say 2 moles of lithium chloride gives 2 moles of HCl gas. So let's see how much lithium chloride we could have gotten out of this reaction. I'm sorry, how much HCl we could have gotten out of this reaction from the lithium chloride. So 55.8 times 2 divided by 42.39 divided by 2. So I get 1.316 moles of HCl gas. Okay, so let's try the other reactant and see what's cooking. So in the case of the other reactant, they don't give us a mass, they give us a concentration and a molarity. So we automatically know how to deal with that. We know that molarity is equal to moles over volume. So if we rearrange this, the number of moles of H2SO4 is going to equal the concentration of H2SO4 times its volume. So the concentration in this case is 2.87 molar times the volume, which is going to be 0.5428 liters. So this is going to equal, so 2.87 times 0.5428. So this is going to equal 1.558 moles of H2SO4. And just like in the first problem, we can't just accept the moles of H2SO4. We have to see how much actually comes out of this reaction, how much HCl we get. Because in this case, you can see that the mole ratio is different. So we know that for every 1 mole of H2SO4, there are 2 moles of HCl. So here we can get that, and 1.558 moles times 2 is going to equal 3.116 moles. So based on this, which one's going to be the limiting reagent? Well, it's going to be whichever one produces fewer number of moles of product. So we can select this as our answer for the HCl because this guy is the one that's going to limit what the reaction can actually produce. Now, in the latter part of this problem, it says calculate the volume of HCl at STP. So we have to basically take moles of HCl, which is going to equal 1.316 moles of HCl gas, and we have to convert this to volume of HCl gas. Now, for those of you who want to be very pedantic about using the PV equals nRT, you can do that. So the only thing you have to remember for this is what STP stands for. So at STP, standard temperature and pressure, pressure is going to equal 1 atm. Your temperature is going to equal 0 degrees Celsius, which is going to equal 273.15 Kelvin. And that's it. That's all you need to have. So knowing PV equals nRT, and knowing that, we can do the calculation. So if we want to calculate volume, volume is going to equal nRT over P, which is going to be 1.316 moles times the gas constant, 0.0821 liters atmospheres per mole Kelvin, times the temperature, which is going to be 273.15 Kelvin, divided by the pressure, which is going to be 1 atm. So volume, in this case, doing the math out, we get 1.316 times 0.0821 times 273.15 divided by 1. So I get 29.5 liters out of that. Now, this is one way to solve it. It's a perfectly legitimate way, but if you want to save some time, the fact that the question says that this is taking place at STP tells you something right away. At STP, we know that 1 mole of a gas will equal 22.4 liters. Okay, will equal 22.4 liters. This is a stoichiometric conversion that you can use at STP. So instead of doing it the way that we did down here, so this is perfectly legitimate. If you did this on the exam, you would still get 100. You'd get 100%. You would lose no partial credit. But you could also simply have done 1.316 moles, and knowing that at STP it's for every 1 mole there's 22.4 liters, you'll get the same answer, which is 1.316 times 22.4, and you'll see that you get the same exact answer, which is 29.5 liters. So they come out to be identical, and that's because at STP only, for every 1 mole there's 22.4 liters. Okay, so that's just something that you can keep in your back pocket as a tool. So this one was option 1, and then this alternate would be option 2. Both give you the right answer. Both are perfectly correct and would give you 100%. But again, we're going back now. We have to remember that whenever we get a problem, we have to make sure that if we have to take into consideration if that's going to be a limiting reagent problem. That's very important. Okay, moving right along. Our next problem is, this is a good one. So this one is a redox reaction where we're going to balance the above reaction using the half reaction method. So the half reaction method, if we remember back to class, is where we look at each species, the one that's being oxidized and the one that's being reduced, and we pull those out, and then we make sure we balance the electrons by looking at how many electrons are transferred. So the important thing to do is to look at what the oxidation numbers are. So in this case, we see that chromium is going to be a 3+ oxidation number. The nitrate, you can see, is on both sides. That's going to be a spectator ion, so you don't have to worry about the nitrate in this case. If you don't see that, oops, there's actually a mistake on the exam. This should be zinc NO3 2. I'm sorry, I will get a corrected exam up. I will correct this exam and then post it with the corrected the correct number. So here we have zinc 0, we have chromium solid, and then here we have zinc 2+ on this side. So what's happening is zinc is going from zinc to zinc 2+, chromium is going from chromium 3+ to chromium 0. So if we want to answer the final question, this is how we would start doing that. But so basically what I'm going to do is I'm going to write chromium 3+, and we're going to write its product is chromium solid. Okay, and this is going to gain 3 electrons because we're going from 3+ to chromium 0. And then the zinc solid is going from zinc metal, so that's 0, to zinc 2+. So we're going to put zinc solid over here. We're going to put zinc 2+ on the other side, aqueous, and this has got to have 2 electrons. Okay. So at this stage we have to balance out the number of electrons. So in this case we're going to multiply this guy by 3 and then this guy by 2. That is so that we have a common number of electrons, which is going to be 6 electrons. So using these multiplication factors, we are going to get that it's 2 chromium nitrate plus 3 zinc solid is going to give, and forgive me, I'm just going to put this down here on the bottom, is going to give 2 chromium solid plus 3 zinc nitrate. Okay, and you can check. So we have 3 nitrates here. We have 2 times 3 nitrates is 6 nitrates. Here we have 3 times 2 nitrates is 6 nitrates. We have 3 zinc and we have 2 chromium. So we're good to go. Okay, so now identify the oxidizing and reducing agents. So all you got to do is flip-flop at this point. What's being oxidized and what's being reduced. So chromium 3+ is being reduced in this case. So if we flip-flop that, the oxidizing agent is chromium 3+. In this case, you could also write and get credit for chromium nitrate. Either one is fine. I prefer this particular one. The reason why I prefer this is because if you look at the net ionic equation, in the net ionic equation, the nitrate's not there. The net ionic equation for this is going to be 2 chromium 3+ plus 3 zinc is going to give 2 chromium solid plus 3 zinc 2+, right? So this is the net ionic equation. So in this case, you see that the nitrate doesn't appear. So my preference is for the chromium 3+. But if you wrote chromium nitrate at this level, it would be okay as well. Okay, so then for the reducing agent, that's just going to be the zinc solid. Okay, so that's how you handle balancing by. Okay, so we're going to pick up with 9. So in this case, this question is a calorimetry question, and it is a calorimetry question that involves heat transfer to 2 different things. So in a calorimetry question, this case it's a bomb calorimeter, so we're taking some hydrocarbon, some amount of hydrocarbon, we're burning it in a calorimeter, and then we are transferring the heat to water and the calorimeter. So in this case, if you want to kind of envision this, we have our calorimeter, inside of it we have some water, and then we have our bomb, and the bomb is going to transfer heat into the water, and some of that heat is going to go into the calorimeter also. Okay, so the walls of the calorimeter are going to absorb some of that heat. So we have to take into consideration the temperature change for both the calorimeter and, meaning the side walls of the calorimeter, meaning the unit itself, and the water. So when we write the equation for this particular one, we're going to say that Q of the reaction is going to equal Q of the calorimeter plus Q of the water. Okay. Now in some cases, it may be that they say the calorimeter absorbs no energy. So it could say the temperature of the water rises, but the temperature of the calorimeter is unaffected. They could say that assume that the calorimeter assume that the water only absorbs the heat. So you have to read these problems carefully, but in this particular question it says the water and the calorimeter rise from 23.83 to 33.15 degrees Celsius. So we have to write equations for both. Okay? So we can just fill this in. So for the Q of the calorimeter, so minus the Q of the reaction is going to, for the calorimeter, they give us a specific heat capacity in joules per degree Celsius. So this is going to be C delta T plus Q of the water, and in this case it is given to us in joules per gram degree Celsius, so this is going to be MC delta T, okay? Because they don't tell you anything about the mass of the calorimeter, they just tell you that if the calorimeter heats up, for every degree it heats up, it's going to be 787 joules. In the case of the water, it says, well, okay, so this is for water, so depending on how much you have, depending on how much mass you have, that mass times this capacity will tell you how much energy it is. So now we can start plugging some things in. So for the Q of the reaction, the C here is going to be 787 joules per degree Celsius. The delta T is going to be 33.15 degrees Celsius minus 23.83 degrees Celsius. Okay, and we're going to add to this the mass of the water. Now we have to make sure that units match in this case. So this is 1.06 kilograms, and then this is grams. So I'm going to convert kilograms, 1.06 kilograms, and I know that for every 1 kilogram there is 1,000 grams. So this is going to be 1,060 grams. Okay. So in this case, that's going to be 1060 grams times 4.184 joules per gram degrees Celsius. And then I'm going to have my delta T, I'll just drop it down to the next line over here, which is going to be the 33.15, 33.15 degrees Celsius minus 23.83 degrees Celsius. Okay? So if we do this out, minus Q of the reaction is going to equal 787 times 33.15 minus 23.83. So this guy is taking into consideration the heat that the sidewalls and calorimeter itself absorbed, and then this part is taking into consideration the water inside the calorimeter and what that absorbed. So we're going to add to that 1060 times 4.184 times, and then again we're going to plug in our delta T, 33.15 minus 23.83. Now I just want to point out that the delta T's have got to be in parentheses. Remember PEMDAS, so you have to make sure you get the order of operations right to get the right number. Okay, so the Q of the reaction in this case is going to equal 48,669 joules. Remember, we have minus Q of reaction because whatever happens over here, so if these guys are gaining heat, the reaction must have lost heat. So we can transfer that minus sign over to here. So our Q of the reaction is going to be minus 48,669. So just for convenience sake, you can convert this to kilojoules, 1,000 joules for every 1 kilojoule. It's not required, but it does make it look better because typically you report your values in terms of kilojoules. And we're going to be looking for a number of sig figs. So in this case, if you do it out, I think you're going to get 3 sig figs. But that's something that, kilojoules. That's just something you have to double check. So you get minus 48.6 kilojoules, but this is not the final answer, okay? This is the number of kilojoules that are produced from 0.87 grams of the sample of hydrocarbon. What this is asking for is calculate the heat of combustion per mole of the hydrocarbon. All right? So that is much different. So what we have to do is we have to divide this number by the number of moles of the hydrocarbon. So to do that, we just have to take our 0.87 grams, multiply this by divide by the molecular weight, which is 91.4 grams for every 1 mole. And from that, we will get 0.87 divided by 91.4. So you get 0.00952 moles. And so here we're going to plug in 0.00952 moles. And if we do our division, we are going to get negative 48.6 divided by 0.00952. So that is going to give us minus 5105 kilojoules per mole. And with sig figs, there's going to be only 2, so this one would be, with sig figs, would be 5.1 times 10 to the third kilojoules per mole, minus 5.1 times 10 to the third kilojoules per mole. So that's your final answer. Okay? Okay, so next up on the hit list is a Hess's Law problem. And since Anna in our class asked to do one where it had a couple of different reactions instead of just 2, that's what I did. So this guy is asking you to calculate the delta H. So basically you could put delta H as a question mark up here for the reaction given above. So we have to rearrange these guys in order to get delta H for the above reaction. So let's start with the first one. So we got to make sure that products are on the product side and reactants are on the reactant side. So in this case it's CS, and that's going to match up with a reactant. So we can rewrite this guy down here. CS plus O2 gas gives CO2 gas. And already I can see that we're probably going to have to multiply this by a factor of 4 to get the coefficients to match up. So I'm going to multiply this by 4, this by 4, and this by 4. So our delta H in this case is going to be the negative 393.5 times 4. So I get minus 1572.8 kilojoules out of that. Now the second one is hydrogen gas plus oxygen gas gives H2O. So here we have H2 gas as a reactant. So we can pop this guy down here as is. 2H2 gas plus O2 gas gives 2H2O liquid. We got to make the coefficients match up, so it looks like we're going to have to do a multiplication by 3 to get the coefficients to match. So I'm going to go ahead and do that. So I'm going to make this into a 6. I'm going to make this into a 3, and I'm going to make this into a 6. Okay, so I've multiplied it by 3. So that means that the delta H here is going to be this negative 571.6 times 3. So that's going to give us negative 1714.8 kilojoules. Now this last guy, we have a problem. You can see that the reactant on this side is actually a product on that side. So automatically I'm going to go ahead and write this down by flipping it. Oops, gives C2H5OH liquid plus 3O2 gas. Okay, so I flipped that, and so I know I'm gonna have to multiply the delta H by a negative 1, and I have to make the coefficients match. So here I have 1 C2H5OH, but up here I have 2. So I'm gonna go ahead and multiply through by 2 to get 4, 6, 2, and 6, and the delta H here. So that means that I flipped it, so that's going to be a negative 1, and then I'm also going to multiply that by 2. So I'm going to take that negative 1367.5 and multiply that by negative 2 to get 2735 kilojoules. So let's just check to make sure that everything works out correctly. We can start crossing some stuff out. So 4CO2 is going to cross out. Let's see, 6O2 is going to cross out. So that's going to be, so we have 7 on this side, so that's going to leave me with 1O2. And our 6H2Os are going to cross out. So if you add all this up, I get 4CS plus 1O2 gas plus what else is in there? Plus 6H2 gas is going to give 2 C2H5OH liquid and nothing else. So this is good. So in order to get the delta H, we're just going to add these guys up at this stage. So the delta H of this reaction is going to equal the negative 1572.8 plus the negative 1714.8 plus a positive 2735, and that gives me a grand total of negative 552.6 kilojoules. So that would be your final answer. Okay. So for this guy, you just got to follow the puzzle pieces, make sure that everything matches up, and you should be good. You should be good to go. Okay, so for problem 11, this is going to be a thermodynamics problem where we are going to have to do a limiting reagent problem. So the tip-off in this case is we have the mass of one of the reactants, strontium carbonate, and we have the volume and concentration of another reactant, hydrochloric acid. Now what's unique about this is that instead of asking how much of something can be produced, it's asking us how much heat is liberated. So we have to basically do a limiting reagent problem, but the final answer, the final target, has got to be in terms of kilojoules produced. So that's just basically we're doing stoichiometry. We have to do two different stoichiometries in order to figure out which one is going to give us the heat produced. So we'll start with the strontium carbonate. So we'll start our first test to see how much heat is produced. So 0.7589 grams of the strontium carbonate. We're going to basically be doing a conversion of grams to moles and then moles to heat. So we can divide this by 147.6 grams for every 1 mole of the SrCO3. And then we know that for every 1 mole of this we get minus 15.2 kilojoules. So for every 1 mole of strontium carbonate we get minus 15.2 kilojoules. So from this we're going to get our answer, which is going to be 0.7589 times negative 15.2 divided by 147.6. So that's going to give us negative 0.0781 kilojoules. Okay. And now the second reagent, they give us a concentration and a volume of hydrochloric acid. So we know how to handle this. Molarity is equal to the number of moles divided by liters. So if we multiply the molarity times the volume, we should get the number of moles. So the number of moles of the HCl is going to equal the molarity, which is 0.871 molar, times 50.5 mils, so 0.0505 liters. So this is going to give a number of moles of 0.871 times 0.0505. So I get 0.043, we could do 0.440 moles of the HCl. And then we have to convert this to an energy. So if we drop that down, 0.0440 moles of HCl. And now we have to do some stoichiometry. So for every 2 moles of HCl, we get minus 15.2 kilojoules. So in this case, we're going to divide this by 2 and then multiply by negative 15.2. So I get minus 0.334 kilojoules. So in any limiting reagent problem, the reagent that produces the least amount of product, or in this case the least amount of energy, is going to be the one that is going to limit the reaction. So for this one, I get a final answer of negative 0.07815 kilojoules is the final answer. So that's just a standard limiting reagent problem, just incorporating things we already know in order to get the energy produced by a reaction. Okay, so last but certainly not least, we come back and we're just going to balance up some redox reactions. These are important to not forget because we did spend some time on them in lab and in lecture, but a lot of times people forget that you have to remember some of the reactivity. So calcium metal and water, this should be calcium solid plus H2O liquid, and we saw this in lab and in lecture, that alkali earth metals, the reason why we call them alkali earth metals is because when you react them with water, they react violently to form calcium hydroxide. So in this case, when we balance this guy up, we have two H's and O's over here, and oh, I forgot one of the products. The other thing too is that in order for calcium to be oxidized to calcium 2+, we also have to form H2 gas. So that is an important product. So in order to get this balanced up, we're going to just need to give this a 2 over here. So that's going to give me my 2 oxygens here, and then we have 2 hydrogens plus 2 hydrogens is 4 hydrogens. So you just have to remember that alkali earth metals form hydroxides and hydrogen gas, as we saw in lab. And this one's a little tough. It is in the textbook, and it's something that you do have to know about, but it is something that you may not have seen explicitly mentioned in class, but it is in the textbook, and it is an example in the textbook. So calcium oxide plus water. Calcium oxide is a basic metal oxide, so this calcium oxides of alkaline earth metals will form basic calcium hydroxide. And in this case, you can see that everything is already balanced up because we have 2 hydrogens here, 2 hydrogens here, 2 oxygens here, and 2 oxygens there. So I don't want you to get super duper worried about this, but I did want to show you these because a lot of people think that lab material does not appear on exams, but in fact it does appear on exams. So there are some things from lab that you should remember. These are also in the textbook, so they count. They were in Chapter 4. But I just wanted to throw this on here at the very end just to kind of refresh your memory that there will be reactions. So this covers all of the questions on the practice exam. And if anybody has any questions, they can get in touch with me through email.